mean value theorem. So far, the important theorem that we have talked about so far has been our intermediate value theorem. We've used it several times. The intermediate value theorem tells us if we have a point here and a point here and the function is continuous, then it's got to cross a certain, a point in between there at some point. So if we can show that happens, then the example that I used for it was that if 3 weeks ago Joe weighed 150 pounds and then this week he weighs 160 pounds, at some point did he weigh 157 pounds? Yes, he did at some point, because if we would assume that's continuous. So mean value theorem is a little bit similar, but it deals with the rates of change of the graph. So if f is continuous on the closed interval AB and it's differentiable on the open interval AB, then there exists a number C in AB such that f prime of C equals f of B minus f of A over B minus A. So that's a lot of words, a lot of math that might not make a lot of sense. What looks familiar to you, though? This stuff right here, what is that? That's slope. And it's the slope between the points A, f of A, and B, f of B. And f of A and f of B are just the y-coordinates that go with A and B. And A and B are the end points of the interval. Okay? So what this tells us is that if we have a graph somewhere and we have a point A right here and we have a point B over here somewhere, the slope of that line through the endpoints, we have to have a point on the graph somewhere where the slope of the tangent is the same, where the derivative is the same. You have to have at least one point. In this particular drawing, it'd probably be 2 points where that slope is, that derivative equals the slope through the endpoint. So we're looking for where the slope of the tangent line equals the slope through the endpoint. The reason this is called the mean value theorem is because the slope through the endpoints is the average value or the mean value for that function. Justice, I'm going to need you to go finish your test. So in Coach Wood's room, he said you could sit there. It's friendly, cozy environment down there with Coach Wood. There is one part that is calculator active, so you will need your calculator for that part. You can use mine. Here you go. It says up at the top of each section. Okay. So this problem is a problem that usually sparks outrage among the class. So Officer Nance and Officer Shoemaker are both waiting on the side of I-77 for speeders. They are exactly 6 miles apart, and the speed limit on the entire stretch of road they are covering is 70 miles an hour. Officer Shoemaker sees a brand new Corvette pass her going 65 miles an hour. She calls Officer Nance to tell him to be on the lookout for the Corvette and gives him the tag numbers. Exactly 4 minutes later, the Corvette passes Officer Nance going 65 miles an hour. Officer Nance turns on his lights and pulls the Corvette over for speeding. Is Officer Nance justified? What should he write the ticket for? Now, so obviously this sparks outrage because he was going 65 at the point that he passed the first cop. He was going 65 at the point where he passed the second cop. He was not speeding at those times. But did he speed in between? Okay, and can we prove it? So we would here for this problem we must assume, or we must assume that we can prove that they are exactly 6 miles apart, that it took exactly 4 minutes, that it was in fact the same car and not another brand new Corvette that looked just like it. All of those things we're going to assume we could prove in a court of law. probably unlikely that cops are actually doing this, but if they could prove it, we need to know if they're justified. So we know that what's happening here is that if we're looking at the graph of the distance that's traveled, we know we're going to put right here, well, actually, I don't need it. For time, we're going to let that point where he passed the first officer, we're going to let that be just 0, 0. So that's right there where he crosses it first. And then if this is distance, no, I don't want distance there, I want time there, sorry. So this is time, and this is distance. Time and distance, I know that at 4 minutes, he had traveled 6 miles. Alright, so up here is my point for that. So if I want to know his average speed, that would be the slope of this line, which is really, I mean, this point is 0, 0. So it's really just taking that 6 miles and dividing it by the 4 minutes. But we can't write a ticket for how many miles per minute somebody was going, so we've got to convert that to miles per hour. So if minutes are on bottom, I'm going to put minutes on top. I'm going to put hours on bottom. And there are 60 minutes in 1 hour. So my minutes can cancel there. So I'm going to have 360 over 4, and that's minutes per hour. I'm sorry, not miles per hour, not minutes. That. Miles per hour. And so 360 divided by 4 is 90 miles per hour. So this guy was not speeding whenever he passed the first cop. He was not speeding whenever he passed the second cop. But he or she was definitely speeding somewhere in between, and not just a little bit either, probably speeding a lot. Because by the mean value theorem, the instantaneous speed of the car must equal 90 miles per hour at least once. For 0 less than or equal to t less than or equal to 4 minutes. So over that 4 minutes, he had to go 90 miles per hour at least once. In fact, since we know he was going below the speed limit at the points where he passed the cops, he was probably actually going even faster than 90 miles an hour in order for the average speed to come out as 90 miles an hour. So what this graph probably looked like is he was probably going slow right here. He really, really, really sped up, and then he slowed. Well, actually, he didn't. We don't need a negative slope. He didn't go backwards. So, like, he's slow slope here, really, really steep, fast right here, and then he slowed back down. So that's probably what his graph actually looks like. And right here, on this piece of graph right here, his slope is higher than 90 miles an hour. So this person was going above 90 miles an hour at some point there. So I feel like if they could prove all of these things without a shadow of a doubt, that this person definitely deserves a ticket, and a big one at that, because that's really fast to be going down the highway. Also, they probably have something that is telling them that the cops are there, either, which Google Maps these days will tell you there's a speed trap ahead. I feel like that's not good for them to do, because, I mean, maybe I appreciate it as a driver, but for the safety of everyone, I don't know if it's good to do that. So something has probably alerted this driver that there is a cop at those points. This is the problem that I like to think of when I think of mean value theorem. So if the average speed over an interval was 90, then the actual instantaneous speed, like the cop sitting on the edge of the road with the radar gun, that's your instantaneous speed. That had to be at least 90, or 90 at least one time over that interval. So I feel like they should get a ticket. Often I have students tell me they really very much feel like they should not get a ticket. But, I think they're going too fast. Alright, so let's look at some problems that you'll get with this. Some of these will be very general. They will not be, some of these will not be, in a situation at all. So, for example 2, we are given the function f of x equals x minus 3 squared on the interval from 0 to 4. Find the c value that satisfies the mean value theorem. Okay, so first of all, anytime we're doing mean value theorem, if you look back to that first slide, you have some conditions that must be met. And I did not really point that out on the last problem, but the speed that someone's traveling, that's going to be continuous. The f is continuous on the closed interval a, b, and differentiable on the open interval a, b. What this means is that your function has to be differentiable everywhere except for possibly at the endpoints. If it's not differentiable at a or b, then that's okay, but everything in between has to be differentiable. So what I would say for example 2, f of x equals x minus 3 squared. That's just a quadratic. Quadratics are continuous everywhere. They're also differentiable everywhere. So, so we could say for this, f of x is differentiable for all real numbers. And since f of x is differentiable for all real numbers, then we can say, therefore, by the mean value, I should write out, mean value theorem. Okay, and then that's where we're going to do our work to find our conclusions. So, so if we want to, the first thing we want to know for our mean value theorem is we want to know the slope through the endpoints. That's our mean value, our average rate of change. So our endpoints are 0 and 4, so we'd say f of 0 would be 0 minus 3 squared, which would give us 9. So that's our point 0, 9. And then f of 4 would be 4 minus 3 squared, which is just going to give us 1. So we have the point 4, 1. And so our average rate of change of this graph would be 9 minus 1 over 0 minus 4. So I would get 8 over negative 4 which is negative 2. Alright, that's my average rate of change. So, by the mean value theorem, there exists at least one C on the interval zero four such that f prime of C equals 2. Sorry, negative 2. So here we're saying there's at least one place on the graph between 0 and 4 where the derivative, or the instantaneous rate of change, equals negative 2. Now, this problem says to find the C value that satisfies the mean value theorem. So, what we're going to do here is we want to know where is that C. Where does the derivative equal 2? So to do this, we'd have to take the derivative. And to take our derivative, we've got f of x equals, x minus 3 squared. So our derivative would be 2 times x minus 3 times the derivative of the inside, which is just 1, so we don't have to write anything there. And so what we want to know is where is the derivative negative 2. And if we want to know where the derivative is negative 2, we're going to set the derivative equal to negative 2. And you could solve this a couple ways. I'm going to divide that 2 off. So x minus 3 equals negative 1. I'm going to add 3. So x equals 2. I guess I really could have said that c, so I could have used c's instead of x's for all that. So at x equals 2, our derivative equals negative 2. That's the point that satisfies the mean value theorem. Okay, questions? I do like to look at this on the graph so you get a picture of what this looks like. So if we were to graph this, y equals x minus 3 squared, and we are looking on the interval. Actually, I'm going to go ahead and 0 less than x less than 4. I think it's squiggly brackets, not. Okay. So right there is the graph that we're looking at. So we're looking at the slope through these endpoints, which I think if I want to put that line there, it would be y equals negative 2x plus 9. Oh yeah, so we're looking at that slope through the endpoints. We're looking for the place where the derivative is the same. So that we found out was at 2 right here. So 2 That's our point right here. If we want to write a tangent line equation for that, we would say y minus f of 2 equals negative 2 times x minus 2. And there's your tangent line. See how that tangent line's parallel, so that we have that same slope of the tangent line in both places. So that just sort of gives you a picture of what we're looking at. Okay, let's do the next one. We are given that f of x equals 5 minus 4 over x. Find all values of c. in the open interval, such that in interval 1, 4, such that f prime of c equals f of 4 minus f of 1 over 4 minus 1. This particular problem is something that you might see. It really doesn't say its mean value theorem at any point. But what we want to know is where the derivative equals the slope through the endpoints, right? Because we've got f of 4, f of 1, 4, and 1. So this is, right here, the slope through 1, f of 1, and 4, f of 4. I like it when they ask problems this way, because a lot of times whenever, especially whenever you're on the exam at the end of the year, whenever you hear verify or show the value that is given by the mean value theorem, you're having to think, what is the mean value theorem? You don't remember what it was. You're getting it mixed up with intermediate value theorem. It gets confusing. This problem, you don't necessarily have to know which theorem you are dealing with if you just sort of follow the directions here. So if you find f of 4 and f of 1, f of 4 would be 5 minus 4 over 4. So it gives 5 minus 1, which is 4. So we have, for our slope here, we would have 4 minus, and then f of 1 would be 5 minus 4 over 1, which is 5 minus 4, which gives us 1. So we'd have 4 minus 1 over 4 minus 1, and we'd end up with 1 as our slope right there. So we want to know where f prime of c equals 1 now. So we first have to find f prime of x. So f of x, I'm going to go ahead and write it this way, 5 minus 4x to the negative 1 power instead of 4 over x. So when I take the derivative of that, the derivative of 5 is 0. Here I'll get positive 4x to the negative 2, which is just 4 over x squared. So that is my derivative. I want to know where that derivative equals 1. I'm going to use the c that since they used the c value here. 4 over c squared equals 1. If you multiply both sides by c squared, 4 equals c squared. You can square root both sides. You get plus or minus 2 is your c, but we are looking on the interval from 1 to 4, so are both of those going to be our answers on the interval from 1 to 4? No, only the positive, so we'll not use that negative there. So 2 would be your answer. Okay, questions? 2 is not always the answer. Just happen to be on both of these problems. Okay. Alright, for example 4, you're likely to get a problem like this on the exam. They like to give these with tables instead of values. So the table below shows certain values for f. A continuous, I should have put differentiable function, not continuous. A differentiable function. Is there a value of an x value on the interval from 0 to 10 such that f prime of x equals 1/2? Alright, so we're looking on the interval from 0 to 10. So we want to look at the average rate of change on that interval. So we want to find, we've got the point 0, 5, and we also have the point 10, 10. Those are the endpoints of my interval here. And so I would say 10 minus 5 over 10 minus 0, and that would give me 5 over 10, which is 1/2. And so this is my average rate of change. And you'll notice that's what they asked us about here. Is there a x value such that the derivative equals 1/2? If we had gotten anything besides 1/2, we would not be able to answer this question. We would have to answer it with a I don't know, because you can't prove it. But this, because this number equals the 1/2 we get over here, we know because of the mean value theorem that there has to be at least one place where the derivative equals the average rate of change. So we would say that f is differentiable. So by the mean value theorem, there must be some x value for 0 less than or equal to x less than or equal to 10, such that f prime of x equals 1/2. In fact, if I were doing this on a free response question, it might actually would have been good for me here to say f of 0 equals 5 and f of 10 equals 10 before I just did these points. That way I'm showing I know that comes from the function there. Okay. All right, last one. F is graphed below. What is the average rate of change of f on the interval from 1 to 5? Okay, so if we look at our points that we have at 1 and 5, you can see, I can see right off. Sometimes I've actually got to do the slope formula, but when I graph that right there, what is the slope of the line through the endpoints? Here is 0, right? Because we just have a horizontal line. So the average rate of change of f on 1, 5, it's 0. Because, and we could do this if we wanted. We could look at, like, your rate of change here. It might be 4, and then it might be 3, and then it might be 2. Right here it's 0. Then it's negative something and negative something. And if we could take every instant and add them all up and divide by however many instants we had, we would get 0. So what happens is all of the positive slopes are canceled out by the negative slopes that you have here. So we just have an average rate of change of 0. If you could think of this being like your finances. Let's say that you're running a business and you deposit money, you lose some money, you gain money back. In the end, you have what you started with. You don't have not gained anything. So average rate of change is just 0 here. B says how many times on the interval from 1 to 5 does the average rate of change of f equal the instantaneous rate of change of f. Okay? So if we look at this graph, how many times is that going to happen? How many times are we going to have an instantaneous rate of change that is the same as our average rate of change, which is 0? Yep, 3. And those, where would they be at, Allie? Right here, you would have a horizontal tangent. Right here, you would have a horizontal tangent. And right here, you would have a horizontal tangent. So all of those where we go from increasing to decreasing or decreasing to increasing, we got to be at 0 before that happens as far as our slope goes. So we would have 3 different places where that happens. This particular instance has a special name. It is called Rolle's theorem. However, it's basically covered by the mean value theorem. Right? It's just a special case of the mean value theorem. So in years past, I've taught Rolle's theorem as a separate theorem. I'm not even really going to really make you know anything about that because it is the mean value theorem just in a particular case. So anything that would be on the exam, if it were a Rolle's theorem problem, you can justify it using mean value theorem. You don't have to know that specific case. So, sorry, Mr. Rolle, you are not as famous as we had maybe hoped you would be. So, we are going to do an assignment for this. Let's see. It is going to be on page 224 is where it begins, and actually it might end up being we're going to do 31 through 30 or 31, 32. Then we will do 37 through 49 odd. And then let's do 57 and 58. Okay, so that'll be your assignment. You hopefully can get it finished before we go, and then also hopefully I will get your test graded so that you'll have that to look at too. Oh, I just flipped this page right here in my planner, and it went to next week where all it says is Christmas break, Christmas break, Christmas break. Every day. It's getting close. We're almost there. Yes. It's 196, I think. Let's see. It might have been 194. That's a possibility. You're probably right. It was probably 194. 1 through 8 were the ones I needed. Did you have those? Okay.